In section 3.3, we take a lot of the things that we did in section 3.2 and we do the converse with them. In fact, we do that over and over and over. First, we have the converse of the same side interior angles postulate. That is one long name for a postulate or theorem. Looking at the outline to the left, it's clear that this won't be the only one with a long name. So what is this long-named converse? First, do you remember the same side interior angles postulate? I know last section was a long time ago. Must seem like ages, but hopefully you remember it. I pointed out in previous sections how so many postulates and theorems are actually if-then statements. Now we want to do the converse of this if-then statement. Now you may start to realize why we covered if-then statements and converses previously. It's almost like we know what we're doing. So what is the converse of this postulate? Taking the converse strictly literally, it would be if the same side interior angles are supplementary, then a transversal intersects two parallel lines. Personally, that seems like it would have been fine to leave alone. I think wording it like that would have been okay, and it would have been the exact converse. However, they decided to play around with the words a little bit, and they came up with this. If two lines in a transversal form same side interior angles that are supplementary, then the two lines are parallel. Okay, fine. They took the actual converse and tweaked it a little bit to make the English a little better. But the basic meaning is still the same. It boils down to this. The same side interior angles postulate starts with parallel lines in a transversal, like this picture here, and given that situation, you can conclude that the same side interior angles must be supplementary. But with a converse, you start with the fact that you have same side interior angles that are supplementary. You don't have any parallel lines yet. That's what you're trying to prove. But the converse of the same side interior angles postulate says, if you do have those same side interior angles supplementary, that is enough to say that those lines must be parallel. You just flip what your hypothesis and conclusion are, the very essence of what a converse is. Now we move on to the next one. This time we have the converse of the alternate interior angles theorem. I will go through the next three pretty quickly as they follow the same pattern as the last one. First you have the theorem from last section. Then we look at the converse of it. They then tweak the wording of it so that we get this official theorem with a really long name. Once again, we don't start with parallel lines. This time we start with alternate interior angles that are congruent. This converse says that the only way you can end up with alternate interior angles that are congruent is if the lines are parallel. Third one up is the converse of the alternate exterior angles theorem. This is just like the last slide, except we switch the interiors for exteriors. We start with the theorem from section 3.2, then we take the converse of it, and then we reword it slightly to get the official theorem. It works just like the last two. Either you are really happy right now that this is fairly easy, or you are really bored right now that they're all the same and just the same as last time except flip. Either way, we're almost done. We had the corresponding angles theorem. Let's flip it around. Decide that no, that wording just isn't good enough for us and come up with this, the converse of the corresponding angles theorem. So this section has been all about flipping the last section off. No, wait, flipping it around. As long as you understand the four basic special angles that are formed with two parallel lines in a transversal from the last section, then this should feel right at home. They are just the converses of them. Instead of starting with parallel lines, these four converses prove that the lines are parallel. There are two main ways that we will use these converses. First, this section is called Proving Lines Parallel. These are the four main ways that we will use to prove that lines are parallel. That word prove keeps coming up. So guess what the first main way is that you will be using these things? Proofs! I know you're excited. Let's say you have a proof like this, but the beginning part is immaterial for this discussion. That's why I have filled it in with a lot of somethings. We just disregard that part. I have said that the four converses from this section are the four main ways to prove lines parallel, and that is absolutely true. Next section we go over a couple more ways that prove lines parallel, but they are extremely minor compared to these four. These four do most of the heavy lifting. They're the ones that show up all the time. These four are the ones that you really need to get down very well. So when you see a proof where the prove line is to prove two lines parallel, you should immediately think to one of these four converses. Somehow, some way, it is more than likely one of them will be the reason for the last step of the proof. So in this case, statement 3 happens to be angle 1 is congruent to angle 2. Looking at those two angles, you should be good at seeing what type of special angles those are. Angle 1 and angle 2 are corresponding angles. Statement 3 says that my corresponding angles are congruent. That's enough to say that my lines are parallel. And the reason is the converse of the corresponding angles theorem. Write small. It's a long name for a theorem. You need to fit it in there. Don't leave out the converse part either. Without that, you are talking about something completely different and it wouldn't work here. So that's an example of the first way you will be using these converses, proving lines parallel in a proof. The proof thing is a blatant and open use of these converses. The other is a little sneakier. In this picture, I'm trying to find the value of x. One common mistake on a problem like this is seeing that x corresponds with a 76-degree angle. And that's absolutely true. They are corresponding, but they are not congruent. In order for that to work, these lines would need to be parallel. And they aren't. Since they are not parallel, those corresponding angles are not congruent. It's a common mistake. We must find parallel lines before those special pairs of angles work, and that is actually the crux of this problem. X is also alternate interior with the 56-degree angle, and that is absolutely true, but we still don't know that they are congruent yet. We again need to know that those lines are parallel, and they are absolutely not marked parallel. But if we could get them parallel, then we'd be on our way to finishing this problem. That 104-degree angle must be useful for something. It doesn't directly pair with the x-degree angle. Those are not related at all. But it must have been given for a reason. But if you notice, that 104-degree angle is same side interior with a 76-degree angle, and they happen to be supplementary. They add up to 180 degrees. And when I have same side interior angles that add up to 180 degrees, I definitely know lines are parallel. I'm going to be using this guy right here. We can use the converse of the same side interior angles postulate to let us know that these lines are definitely parallel. And once those lines are parallel, then I can go back to my alternate interior angles. And now that the lines are parallel, I can say that x and 56 must be the same, so x is 56 degrees. That's the second main way you will be using these converses. One of the converses will allow you to mark some lines parallel in your picture, and then those parallel lines will let you solve a different problem. And last but not least, we have a flow proof. A flow proof is basically another way to do a proof. Some prefer it over the paragraph proof or the two-column proof. To show you what it looks like, let's start with a standard two-column proof. This is the proof of the converse of the alternate interior angles theorem. We obviously can't use the theorem to prove itself, so we had to go about it another way. We start with the alternate interior angles that are congruent. Angle 1 and angle 2 are alternate interior, and they are given that they are congruent. With those congruent alternate interior angles, we need to find a way to prove the lines are parallel. The first step is to get your free points. Now we need to figure out what else we know about the picture. Angle 2 and angle 3 are a special pair of angles. They are vertical. So I can say angle 2 is congruent to angle 3. The reason is the vertical angles theorem. Looking at the first two statements, I have angle 1 congruent to angle 2 and angle 2 congruent to angle 3. That should look like a familiar pattern. It's the transitive property. The transitive property lets me say that angle 1 is congruent to angle 3. The reason is the transitive property of congruence. For the record, you could have used the substitution property here just as easily. Now we have angle 1 and angle 3 congruent. If you look carefully, you will notice that those are corresponding angles. We have corresponding angles that are congruent. That's something special. We can say our last step. Line A is parallel to line B due to the converse of the corresponding angles theorem. So that's the proof done in two-column form. Now I will show you what the same proof looks like in flow proof form. You start with the same given and prove lines, but there is no chart or column. Instead, you put pieces of information floating out there with their reasons underneath them. So our first line would be just floating out there like this. Then we did the vertical angles, so our second line floats out there like this. Now we used both of these two statements together to come up with our next line. So we put arrows showing how our logic flowed from those two statements to come up with our third statement. That statement alone was how we could get to our final statement. So our logic only flowed from that one spot. And that brought us to our final conclusion. And that's what the equivalent proof looks like as a flow proof. It shows very well how statements combine together to come up with the next piece in the chain. That is by far its biggest strength. You do have to be careful about your reasons. They often need to be abbreviated like they are here so you can fit them all in. On super complex ones, it looks like spaghetti has been dropped on your paper. But for beginner proofs that are pretty simple, where you need help seeing how logic is flowing around, a flow proof isn't bad.